Welcome to the Deep Dive, the place where we take that absolute fire hose of information, everything from dense technical papers on resource optimization to strategic guides on the new role of the product manager and even foundational ethical white papers. And we distill it all down into the essential, actionable knowledge you need.
Today, we are mapping the current state of the AI transformation. And this isn't about the glossy headlines. Our sources give us this incredible kind of 360-degree view. We're tracing the shift from the highest level, corporate philosophy all the way down to the gritty reality of milliseconds and dollars in deployment.
And the professional demands that come with it.
And the evolving technical and professional demands, absolutely.
That's right. Our mission today is really to give you that shortcut to being well-informed on this entire landscape. We're going to trace how AI is changing the game for product development, how the infrastructure manages these, almost impossible trade-offs, and what's now expected of you, the professional, inside these major tech companies. AI has, I think we can all agree, moved way past being a futuristic promise.
Yeah.
It's the present-day necessity shaping every single product decision.
And we can already see two huge interconnected vectors that are driving this whole transformation. And we really have to understand these up front. First, there's the fundamental shift in how we design systems. This inevitable move away from deterministic, rules-based logic to systems that are inherently probabilistic.
Okay, so if I'm tracking that right, what you're saying is the output is no longer a guaranteed if X, then Y.
Exactly.
Because the system is always learning and adapting. So instead, the result comes with a confidence score, like if X, then Y, with, say, 85% confidence. And that uncertainty, that probability, that just fundamentally changes how products are managed. We'll definitely have to dive into how that impacts things like bug reports later.
Precisely. And the second vector is this complex trilemma that governs all AI infrastructure. The challenging and often, frankly, painful trade-off between speed or latency, minimizing cost, and ensuring quality.
Speed, cost, and quality.
Those three. They are locked in this constant battle that really defines the usability and, maybe more importantly, the affordability of every generative AI application today.
Okay, so let's start unpacking this transformation at the foundational layer. Before we get into those complex probabilistic deployments, we need to make sure we're all speaking the same language. AI has become this, sprawling, often misused umbrella term.
Absolutely. The terms get confused constantly, but for anyone who's, designing products or managing technical teams, understanding this strict hierarchy AI, machine learning, and then deep learning, it's just crucial. They are not interchangeable.
Let's start at the top then, the biggest umbrella. Artificial intelligence, AI. So this is the broad goal, the whole field, right? Teaching machines to do tasks that would normally require human intelligence.
Things like decision-making, visual perception, recognizing speech, translation.
All the big stuff.
Right. And the everyday examples are everywhere, but they're often simple in concept, like your virtual assistant, whether it's Siri or Alexa or Google Assistant. Those systems perform intelligent tasks, but the methods they use can vary wildly. That's the big AI bucket.
Okay, so let's step one level down. Now we get to machine learning, ML. This is a specific method inside of AI. So instead of explicitly programming a machine with millions of rules, ML systems learn directly from huge amounts of data.
And they improve over time. The key is they improve without being explicitly programmed for every single outcome.
Right, so a classic example of this in action would be an email spam filter.
Perfect example. It didn't start out perfect. It learned over years from seeing which emails you marked as spam and which you didn't. It finds patterns in the data, certain keywords, sender domains, types of links, and it uses those patterns to classify new mail. It's always adjusting its filters.
Getting better, or sometimes worse, depending on the data it's seeing.
Exactly. Which brings us to the cutting edge. What's powering most of the excitement today? Deep learning, DL. This is a specialized, very modern subset of machine learning. It uses these multi-layered neural networks, we often call them deep neural networks, to process incredibly complex, unstructured data.
And this is what gave us the whole generative AI revolution we're in now.
It is. It's what handles language, advanced image recognition, video generation. When you use facial recognition in your photo app, or when Gemini generates a piece of text, that's deep learning. It handles tasks where the features aren't easily defined by a human, but are instead learned by the network itself.
So the hierarchy is key. Deep learning is a type of machine learning, which itself is a part of the broader field of AI.
That's the framework.
And having that clarity is the baseline, because when we talk about the major industry players, they're often competing across all three levels of this hierarchy.
Oh, absolutely. The competitive landscape is just intensely dynamic. You've
Yeah.
got OpenAI pushing the frontier with models like GPT-4o. You have Anthropic focusing really heavily on safety with Claude. Meta is pushing open source innovation with Llama 3.
Which the whole world can build
A
on.
whole world. And then you have contenders like Mistral and Cohere offering these highly customizable enterprise solutions.
But our sources really zero in on Google's strategy, which it seems isn't just about a single model. It's an entire comprehensive AI stack. It's designed to be leveraged at every layer, from the chip all the way up to the end user app.
Let's run through that stack because it really shows their ambition.
Mm.
At the foundation, the generative models, they have Gemini, which they position as their most intelligent, multimodal model for complex reasoning. Then
Mhm.
you have Gemma, which is their family of state-of-the-art open models.
Right, which lets developers use powerful, secure AI without that proprietary licensing overhead.
And the innovation goes way beyond text. They have these specialized models for different media. There's VO for video generation, Imagen for high-fidelity text-to-image, and Lyria for generating music and audio. They're explicitly trying to cover the entire multimodal spectrum: text, code, image, video, audio, all of it.
And these are the models that power the applications that you, our listener, are probably interacting with every day. Gemini is the proactive assistant, but let's look at a more specialized tool, like Notebook LM. That's positioned as a research and thinking partner.
That's a fascinating example of augmentation. Notebook LM doesn't just summarize documents. You feed it your own source documents, and it acts as an expert on only that specific information.
So you could ask it to generate insights or draft an outline connecting ideas across, I don't know, 50 different PDFs and notes you've collected.
It completely replaces the old index card system for a researcher or writer. It just dramatically speeds up that synthesis process.
And then this utility extends into the professional workspace.
hmm
We see AI assistants baked right into Workspace with things like Help Me Write in Docs or Gmail.
And that's not just spell check anymore. This is about augmenting productivity drafting emails, summarizing these massive threads, turning bullet points into a report. The whole suite becomes a personalized collaborator.
And then for the builders, there's a full toolkit. Google AI Studio for developers to prototype things quickly, and Vertex AI as the big comprehensive enterprise platform. That's for security, control, all the management tools you need for a large-scale corporate deployment.
It really is a full stack end-to-end approach.
But a company that builds and deploys technology this powerful at this kind of scale, they have to address the profound ethical implications.
They do. And Google's approach is explicitly grounded in their original mission, organizing the world's information and making it universally accessible and useful. They recognize that if AI introduces widespread harm, it just completely violates that core mission.
So their strategy forces them to be two things at once: incredibly bold in innovating and deploying these products, but also profoundly responsible in how they develop the AI to safeguard users.
Let's look closely at the three pillars that define this commitment, starting with the one that drives that innovation engine: bold innovation.
This basically means developing AI that assists, empowers, and inspires people in almost every field. The sources really emphasize accelerating scientific discovery in biology, medicine, chemistry, and driving economic progress.
But here's the critical tension, right? How do you reconcile that boldness with safety? The key caveat in their framework is that models and applications can only be deployed where the likely benefits substantially outweigh the foreseeable risks.
So it's not enough for it to be slightly useful,
No, it requires a rigorous, upfront risk-benefit analysis.
which flows right into the second pillar:
Yeah,
responsible development and deployment. They acknowledge that AI is an emerging technology with continuously evolving risks, so they have to pursue responsibility through the entire life cycle, from the initial design, through testing, to deployment and iteration.
and this isn't just philosophy. It translates into concrete steps. This means implementing human oversight, doing rigorous due diligence, and building robust feedback mechanisms that align with international law and human rights. It means investing heavily in safety tuning and security research,
Which can sometimes slow down release cycles.
which often does to ensure the model is properly aligned.
We see that practical application in their development frameworks. They explicitly mention rigorous design, testing, monitoring, all to mitigate harmful outcomes. And crucially, this includes actively working to avoid unfair bias, promoting privacy, and ensuring respect for intellectual property rights, which is a huge challenge in the LM space.
Definitely. And finally, the third pillar: collaborative progress together. The idea here is really pragmatic. The challenges posed by AI, from global regulation to infrastructure security, they're just too big for any single company to solve alone.
So they commit to two things. First, empowering others to harness AI by developing it as this foundational technology. And second, actively engaging with researchers, governments, and civil society to address these massive shared challenges. The goal is to accelerate progress for the whole ecosystem, but in a safe and sustainable way.
So with those foundational models and ethical commitments in place, we can now turn to the person who sits right at that intersection of business, technology, and the user, the product manager. This role is going through a radical transformation.
And this is driven by that first major vector you mentioned, the shift from deterministic to probabilistic systems.
Exactly.
Let's really nail down that distinction, because it's the difference between managing, say, a simple app feature and managing a complex learning system. In the past, the traditional PM worked with deterministic, rules-based logic. You build a checkout button, you expect it to work the same way every time.
The output was guaranteed. If a traditional PM system malfunctioned, like the sort search results by price feature failed, it was a true bug. You could trace it to a specific line of code.
And the fix was clear. Find the error, rewrite the rule.
But the AI PM lives in a completely different world, a world of probabilities, data dependencies, and evolving model behavior. Their system manages ambiguity. The output for rank these results based on user preferences can change from moment to moment. They are managing systems that actually learn.
So this changes how they even handle failure. If a user complains the search results were irrelevant, it might not be a bug in the code.
It might be a data quality issue, or the model reflecting a learned but undesirable bias from its training set. Fixing it requires data science and retraining, not just a quick code patch.
And this probabilistic nature, it completely rewrites the product requirement document, the PRD. In the old days, the PRD was prescriptive. If the user is logged in, show the top 5 results sorted by date. Precise, rules-based logic.
But the AI PM's requirements are all about defining desired model behavior and measurable outcomes under tight constraints. Our sources give a perfect example of a modern AI PRD requirement. Utilize user activity history to surface personalized results, ensuring at least 80% relevance based on human-rated evaluation with a latency under 200 meters.
Notice that shift. The PM isn't telling the engineers how to sort. They're defining the required level of user satisfaction, that 80% relevance, and the speed constraint, under 200 meters. Success is measured by these behavioral metrics, not just by shipping a feature.
And that requires a completely new level of technical fluency. To succeed in this ambiguous world, AI PMs have to understand the core mechanics of large language models. They don't need to train them, but they have to understand the building blocks to design products and talk credibly to engineers.
Okay, so let's start with that foundational understanding of LLMs. They're trained on billions, sometimes trillions of words. They're fundamentally pattern-matching machines, incredibly good at mimicking human responses.
But the core mechanism, which often seems like magic, is actually quite simple. Token prediction.
Think of it like super advanced autocomplete.
That's it. The model breaks everything down into tokens words, parts of words. Given the sequence of tokens it's generated so far, its entire job is to calculate the statistical probability of what the next most appropriate token should be, and then it picks it. And it just repeats that process.
And it's just the sheer scale of the training data and the complexity of the neural network that makes this prediction feel like human intelligence. But at its heart, it's a statistical guess.
And that guess is controlled by parameters that are critical for product design. The first one is the context window. As LLMs have grown, so has their memory. The context window is how much information the model can consider at any given moment.
And the size of that window is a core product design decision. If you're building a research assistant, you need a massive context window, so a user can paste in 5 long documents, and the model can remember the first one while answering a question about the last one.
A larger window allows for much longer, more consistent conversations, but, and this is a big but, it also increases the cost and latency per token. It's a trade-off.
Always a trade-off.
The second critical parameter is temperature. This is basically the control knob for the model's creativity or its randomness. It's a measure of how far the model is allowed to stray from the highest statistical probability when it's picking the next token.
So if a PM sets the temperature really low, say close to 0, the model will always choose the most probable, factual, predictable word.
Which is great for tasks like high-fidelity summarization.
But if you crank the temperature up high, the model is encouraged to pick less probable, more inventive token.
Right. perfect for brainstorming or creative writing, but it dramatically increases the risk of hallucination or just being plain wrong.
Understanding these concepts leads directly into the unique responsibilities of the AI PM. Their job moves beyond the traditional feature roadmap to proactively managing data and learning behavior.
And the first unique responsibility is data scoping and strategy. The training data is the core product asset, and the PM has to treat it that way. They need to deeply understand data availability, how it's labeled, and whether it contains unacceptable levels of bias. They're often responsible for guiding the creation of synthetic data to fill in the gaps.
Next up is the radically different process of testing and evaluation. Old school A/B tests, did the user click the button? They're just not enough anymore. The AI PM needs fluency in model-centric metrics that gauge the technical performance of the system itself.
So this means understanding concepts like precision of all the results the model said were relevant, how many actually were, and recall of all the truly relevant items, how many did the model actually find.
And the F1 score.
The F1 score is so important in the AI PM's toolkit because it's the harmonic mean that balances precision and recall.
Why is balancing them so important?
Because you can always get perfect recall if you just return every single result, including all the irrelevant ones. And you can get perfect precision if you only return one result that you're absolutely sure of, but then you miss everything else. The F1 score forces the model to find that healthy balance, which is a critical constraint when you're defining a successful product.
And the evaluation process itself is layered. It requires offline evaluation, then shadow mode testing running the new model alongside the old one without users seeing the results, just to measure it internally.
And continuous human-in-the-loop reviews to make sure the quality actually aligns with human intuition.
And finally, there's the ongoing responsibility of monitoring and retraining. AI features are dynamic, they're not static. The PM has to manage model drift.
Which is that insidious performance degradation that happens when the real-world data the model sees after deployment starts to diverge from its training data.
So like a model trained on pre-2020 internet data, if you deploy it in 2025, it's going to struggle with new slang, major world events, cultural shifts.
And its quality will degrade slowly and subtly. The PM has to establish monitoring pipelines and ensure the engineering team has a robust retraining strategy to address that drift before it really impacts the user experience.
So the AI PM is this strategic translator, ensuring that all the business and user constraints, the required quality, the ethical commitments, the need for low latency and low cost, are all aligned with the probabilistic capabilities of the model.
That deep focus on constraints, cost, quality, and latency brings us right to the hyper-technical challenge of deployment. This is the world of infrastructure, where model size, budget, and speed all collide.
And the fundamental tension here, it's all defined by model size. A larger LLM, say one with 70 billion parameters, it offers significantly higher quality and deeper reasoning. But
that scale requires immense computational power, which translates directly into higher infrastructure cost and slower response times higher latency.
let's illustrate this critical trade-off with the data from our sources. Imagine a simple factual query. Which scientific treatise was published in 1687? A smaller, efficient model, like Llama 3.2, instruct with 1 billion parameters, it can answer this correctly and quickly.
But if you decide, just for simplicity, to route that simple query to a massive model like Llama 3.1 Instruct, the 70 billion parameter one, the cost penalty is just severe. For that simple query, the larger model incurs 7 times the cost and 15 times the latency.
That's insane.
That level of inefficiency is completely unsustainable for any application handling millions of queries an hour.
But the reverse scenario proves you can't just use the small model for everything. If you give it a complex reasoning prompt, like asking for a sketch of the proof for Fermat's last theorem, the smaller 1B model might just confidently hallucinate a flawed proof.
Whereas the massive 70B model correctly recognizes the problem's complexity and gives you a valid, high-quality proof sketch. It demonstrates sophisticated reasoning. So this shows the critical need for intelligent traffic management. You have to assign each prompt to the cheapest and fastest model that is just good enough to deliver the quality you need.
The challenge of managing this triple constraint, speed, cost, and quality, is what led to the development of these really sophisticated routing systems. Our sources highlight one specific technical solution: SCORE, the smart cost and latency optimized router.
SCORE's mission is elegantly complex. It has to maximize response quality under strict user-specified cost and latency constraints. It's built to manage these compound AI systems that use multiple LLMs of varying sizes and
So,
capabilities.
so think of SCORE as a high-speed graphic cop inside your data center. When a new prompt arrives, the cop has to decide instantly, do I send it down the small, fast, cheap local road, the 1B model, or the big, expensive, sometimes congested highway, the 7D model?
And the decision has to maximize the user satisfaction, the quality, while respecting those time and budget rules.
The core technical problem, as you said, is incomplete information. When the prompt arrives, the router doesn't know the exact quality or the precise cost or latency, because that all depends on how long the model's response is going to be.
It has to predict the outcome. So SCORE relies on two critical estimations that are generated by these lightweight predictive models. They use a Distilbert-based approach.
And that's key, right? Distilbert is chosen because it's a smaller, faster version of the powerful BERT model. It's like a specialized, efficient traffic analyzer that doesn't incur the massive overhead of running the full-size models just to make a routing decision.
The first prediction is crucial: response quality. This estimator rapidly assesses the prompt's complexity and predicts the quality of the response on a scale from 1, very poor, to 5, excellent. This prediction helps the writer decide if the prompt must go to the expensive model or if the cheaper one will do.
And the technical paper noted that the quality scores they used for training these predictors were actually generated by GPT-4o Mini.
Right, which just shows you the layering involved.
Mhm.
Even the training of the routing system relies on another specialized model to act as a consistent human quality judge.
Okay, what's the second prediction?
The second prediction is response length. This is essential because cost and runtime are fundamentally proportional to the response length. It directly informs the cost calculation and the runtime estimation.
So the routing decision is then formulated as this complex, real-time optimization problem. SCORE maximizes the net benefit by factoring in that predicted quality, the known cost per token, and the predicted latency. But then it gets even more complicated when you add the user policy.
And this is where the product manager's strategic vision comes right into the infrastructure layer. Users can provide specific weights, dollars and dollars, to prioritize cost versus latency. If the product is an interactive chatbot, the user sets a high latency weight, telling SCORE to prioritize speed above all else.
Even if it means sacrificing a tiny bit of quality or slightly increasing the cost.
Exactly. The router adjusts its formula to respect those weighted constraints.
And this is the part that often gets missed. Latency isn't just the processing time. It critically includes the waiting time from system load, the queue delay.
That's such a key point. Even if the small 1B model is theoretically fast, if it's currently swamped with requests, the queue delay might push the total latency past the user's limit.
So the router has to constantly monitor the load balancing and queue stats across all the models. It might actually be faster, paradoxically, to send a simple request to the bigger, more powerful model if its queue is short.
The intelligence is in the dynamic adaptation, not in fixed rules.
And the preliminary results from testing SCORE, they validate this approach beautifully. The experiments used the two-model system, Llama 3.21b and Llama 3.170b, running on high-performance NVIDIA H100 GPUs.
And the setup itself was sophisticated. They had two GPUs dedicated to the massive 70B model, and the third one hosted the smaller model and all the little predictive, Distilbert-based estimators.
And the key finding was that SCORE significantly improved the mean response quality compared to a baseline router that just ignores predicted quality. By intelligently routing prompts, it maximizes the quality outcome across all requests while rigidly sticking to the cost and latency limits.
This just demonstrates the tangible efficiency gain for the business. If you loosen the cost constraint, SCORE automatically routes more borderline prompts to the stronger model, increasing overall quality. If you tighten the latency constraint, it prioritizes queue stats and load balancing to ensure speed. It's what makes LLMs financially viable at scale.
We've established the technical demands, the economic constraints. Now we pivot back to the ethical and human consequences of deploying these powerful systems, especially when they automate really critical functions like talent assessment.
Right. AI-powered interview tools are a perfect, and I think cautionary, case study in AI failure points and real-world determination. When you introduce automation into these subjective processes, the probabilistic nature of the system can introduce significant and very hard-to-detect bias.
Our sources identify 5 distinct causes of bias that can creep into these systems. And it's crucial to understand the distinctions. because the way you fix it changes based on the source of the problem.
The first, and probably the most common, is historical bias. This one is so insidious because it's a direct reflection of ingrained societal inequalities that are already present in the training data.
So if a company historically hired only men for an engineering role, the AI, trained on years of that hiring data, will logically conclude that male candidates is a highly predictive feature for success.
And it perpetuates and automates that bias against female applicants.
Okay, what's next?
Next is algorithmic bias. This happens when the system is perfectly optimized but for the wrong thing. For example, an AI hiring tool might be optimized to maximize new hire retention. It learns that candidates with continuous employment history tend to stay longer.
But in doing so, it might accidentally penalize candidates with resume gaps from, health breaks, parental leave, caregiving.
I think is completely irrelevant to the actual job requirements.
We also have sample bias. This isn't necessarily about history, but about data coverage. If the training data set has disproportionately more data about one group, say, more high-quality video data for candidates from affluent areas, the AI will naturally perform better and score those candidates higher.
It leads to unintentional discrimination against underrepresented groups just because it has more reliable information on the majority group.
Then there's the feedback mechanism, which can lead to confirmation or amplification bias. If a company has a cultural preference for, say, extremely quick, confident speakers, the AI will confirm that pattern. But worse, as AI runs at scale, it doesn't just replicate those human biases.
It can magnify them across thousands of applications. It turns a simple human preference into wide-scale amplification bias.
And finally, the very human oversight failure, automation bias.
This one is psychological. Recruiters, when they're presented with a decision from a complex, expensive AI, they tend to place too much unquestioning trust in it. They assume the AI is objective.
So if the system produces an illogical or unfair decision, the human oversight might fail to investigate, allowing biases to go unchecked simply because the AI said so.
This demands a structured solution framework. We can't just turn off the AI, but we have to actively mitigate these risks. Our sources detail 5 steps to address bias in AI hiring, and they apply pretty generally to any high-stakes AI deployment.
Okay, step 1.
Step 1. Diversify training data. This is the fundamental requirement. The data sets must be aggressively complete and represent a wide range of candidate groups, different demographics, ethnicities, accents, communication styles.
You have to proactively collect and audit the input data to make sure it doesn't already contain the historical bias you're trying to avoid.
Step 2. Reduce focus on non-job-related metrics. The PM has to work with HR and data science to rigorously identify which criteria truly correlate with on-the-job success and which are just cultural artifacts. Tone of voice might be irrelevant for a back-end engineer, even if the AI found it predictive.
Step 3. Provide alternatives and accommodation. AI interviews create accessibility barriers. If a candidate has poor internet or a disability that affects their speech patterns, the AI might unfairly disqualify them.
So companies have to prepare alternatives like written interviews or moving directly to a face-to-face human meeting if the AI flags a candidate as an outlier.
Step 4. Ensure robust human oversight. The recommendation is clear. AI should augment, not replace, the most subjective parts. Use it for early, high-volume screening, but transfer the process to human recruiters for shortlisting and later rounds.
It maintains those essential human checks and balances. And step 5. Audit regularly and proactively. Organizations need to move beyond just fixing problems after they happen. This means frequent, proactive bias checks with specialized tools. You have to establish and track fairness metrics like demographic parity to make sure the hiring funnel isn't disproportionately affecting one group.
And use adversarial testing, deliberately feeding the system flawed data to test its failure points.
Exactly.
Now, let's pivot from hiring bias to an equally critical risk in product discovery. The danger of outsourcing your thinking doesn't stop at HR. It pervades the whole process of innovation.
Right. The goal of product discovery is to increase your hit rate for creating real customer and business value by deeply understanding specific, unmet human needs.
And the fundamental warning here, especially for product managers relying on LLMs, is crystal clear. Don't replace real humans with generative AI in discovery.
Generative AI excels at creating generalizations and plausible fiction. It does not excel at creating the messy, specific human stories that drive genuine innovation.
Our sources give this brilliant illustration using a hypothetical Netflix customer. If you ask a generative model about common pain points, the output is generic. App is hard to navigate, costs are too high, want more content. It's just a synthesis of common knowledge.
And when you push the AI to generate a specific rich user story, the kind product teams use to build empathy, the result is hollow. The source calls it the crate and barrel showroom user story. The AI describes a user who's always comfortable, has a glass of my favorite drink, and only experiences minor interruptions.
It lacks any genuine conflict or nuance.
But real human stories are the competitive differentiator. The anecdote of the user trying to watch the Olympics, getting distracted by YouTube, accidentally seeing the results on their phone, and realizing the joy is ruined. That messiness is specific. It's actionable. It helps you design better features. Generative AI struggles to produce that unique insight because everyone has access to the same generalized training data.
The second major warning is, don't use AI to replace thinking. Artifacts like opportunity solution trees or story maps, they're just the byproducts of discovery. The real value is the rigorous thinking process, the team alignment, the debate required to create them.
If you outsource the first draft of an opportunity solution tree to an AI, you're inviting what's called social loafing. The team just defers to the AI's limited, generalized perspective. The valuable hard work of getting the engineer, the designer, and the marketer to argue about priorities is completely lost.
So the AI, which is based on statistical averages, ends up dominating the product strategy conversation just because it got there first.
The recommendation, therefore, isn't to ban AI, but to use it to augment the team. Treat it like a highly efficient, specialized team member. Use it to analyze massive data sets, like categorizing 300 open-ended survey responses into themes.
But the crucial step that has to follow that augmentation is always check its work and iterate. The source analyst had to push the AI several times, shifting from raw counts to averages, then insisting on normalized averages to get reliable, unbiased analysis. If you outsource the critical thinking required to know what to ask, the results will be misleading.
Good discovery, leveraging specific human stories, and critical team alignment remains a competitive advantage that just cannot be automated away.
This high-stakes, technically complex, and ethically fraught environment translates directly into extremely high professional expectations, especially for product managers trying to get roles at top-tier tech companies.
Absolutely. When companies like Google are managing vast multi-model routing systems like SCORE and balancing these massive ethical commitments, they need PMs who can operate at scale and manage that complexity. Google, in particular, focuses on finding candidates who can truly own a product vision, prioritize complex roadmaps, lead cross-functional teams, and demonstrate 10x thinking.
And 10x thinking isn't just a buzzword. It means setting ambitious goals that aim for transformative impact. Solving a problem 10 times better or cheaper, not just 10% better. It requires a willingness to embrace risk.
Which aligns with their commitment to a culture of learning, specifically a blameless post-mortem culture for failed experiments. Google embraces rapid experimentation and accepts that not all ambitious projects will work out. The PM needs to be able to analyze failure systematically and apply that learning quickly without fear of personal blame.
But let's talk about the technical bar, because this is a huge differentiator. Our sources confirm that Google explicitly includes dedicated technical questions with system design components, often in a specific technical round during the on-site interview.
And this is mandatory for PMs who are managing algorithmic products.
Candidates aren't expected to write production code, but they have to demonstrate the ability to think through complex system block diagrams and technical trade-offs. You need to be able to collaborate effectively with software and machine learning engineers on their own turf.
The required knowledge level is what's called a system block diagram level. This means you need to be able to sketch and discuss the high-level architecture, identifying components like the load balancer, the database structure, the messaging topic, the data pipeline. You need to know what data those pieces convey and how they talk to each other.
So, for example, if you are asked to design a system for real-time translation, you need to understand where the LLM inference happens, how caching would reduce latency, where a predictive model like SCORE would sit to route traffic, and how you would handle the massive data flow for continuous training.
It's all about architecture and trade-offs, scalability versus cost, consistency versus availability.
For listeners who are preparing for these high-stakes product design and product sense questions, our sources provide a really clear, structured, 6-step framework. It's designed to apply logic to ambiguity and ensure you hit all the criteria the interviewer is looking for.
Step 1 is always to clarify. Before you suggest any solutions, you have to define the constraints, the goal, and the scope. What's the budget? The time frame. Is the primary goal adoption, revenue, or satisfaction? You have to confirm these details with the interviewer.
Step 2 is context. Just take a brief moment to set the scene. Who are the competitors? How are people solving this problem today? It shows you're not designing in a vacuum.
Step 3 is users and pain points. This is the empathy phase. You need to brainstorm and segment users, but critically, avoid focusing on demographics like age. Focus on characteristics. The busy working professional, the first-time parent. Then, for your target segment, identify at least 3 related pain points, the gaps that current solutions aren't solving.
So if you were designing a new financial product for that busy working professional, the pain points might be 1. Lack of time to manage investments. 2. Safety concerns about algorithmic advice. And 3. Difficulty aligning spending with long-term goals.
Step 4 is solutions. Propose at least 3 distinct solutions that directly solve those pain points and tie back to the original goal. The framework encourages having moonshot ideas. Don't be afraid to suggest something that needs R&D, and if you're interviewing for a big company, mixing multiple company products into one solution.
Step 5 is prioritization. You have to articulate a clear rationale for which solution to tackle first. Prioritize based on the objective, the pain point solved, and the viability or feasibility. And if you propose a physical product change, prioritize that first, since software updates are always easier to push later.
And the final step, 6, metrics. Define how you'll measure success by linking metrics directly back to the goal from step 1. You should think about user metrics, like downloads or retention, and product metrics, like the time it takes a user to discover a feature or the success rate of the AI in providing a high-quality answer. It demonstrates comprehensive product ownership.
So as we synthesize everything we've mapped out today, from these high-level strategic principles all the way down to the raw complexity of the infrastructure, 3 major takeaways seem to define this current transformation.
First, I think, is the cognitive shift for every professional. The AI era just demands that we think probabilistically, not deterministically. Success is measured by managing uncertainty and data dependencies, and that requires a new kind of rigor from everyone.
Second, technical depth is now mandatory, especially for decision makers. Understanding those resource constraints, cost, latency, and quality, that is the primary bottleneck for deploying AI at scale. You have to be able to manage those trade-offs.
And third, ethical responsibility and just genuine human critical thinking have to be the firewall against automation. We have to actively audit for bias in every deployment, and we have to resist that impulse to outsource the essential human element of product discovery, which requires real empathy.
Which brings us to our final provocative thought for you to consider. If the most advanced AI systems, like SCORE, are designed to maximize a predicted quality score, judged on a scale of 1 to 5 under ruthless time and budget constraints, what we're really building is a system optimized to produce the cheapest, fastest, most acceptable response.
So the question is, what tasks are so uniquely human, so messy, or so nuanced that we cannot allow their evaluation to be reduced to a 1 to 5 efficiency score, regardless of how computationally clever the router becomes?
That is the essential constraint we all have to manage going forward. Thank you for joining us on the Deep Dive.